probably all heard of bleach before. Awesome disinfectant, great use around the kitchen. Probably wouldn't want it in your morning coffee though. Yeah, you might have also heard of ammonia, another great natural disinfectant. It kills a lot of forms of bacteria, except it could get in your morning coffee because it's coming out of your tap water. And if high enough doses of it get into New Zealand fresh waters, it can have some serious effects. Now, ammonia is a natural chemical. It's a byproduct of nitrogen, and it's considered a nitrogenous waste. This means if nitrogen gets into something like a body of water, it can eventually turn into ammonia. Now, we do have some benefits. It is a great natural disinfectant. We use it in ACs and refrigerators, and even fertilizers under the right conditions. However, when it gets into our waters, it's a very different situation. This is not something that you want to consume. Our bodies cannot process it under high concentrations. It's just as harmful to us as it is to all forms of marine life that are in the same body of water. And if there are high enough concentrations in our drinking water, it will be considered completely unsafe to drink. Now, governments are very aware of this. However, we have had problems in the past of New Zealand having too high-level ammonia levels in New Zealand waters. Back in 2013, New Zealand exports lost $5 to $10 million after 42 tons worth of milk powder was created and shipped to China. However, when they checked the ammonia levels, it was far too high to be considered safe for commercial use and was so discarded. Even as of last month, the Ministry of Local Government has continued to try and improve and create better water policies for rainwater, wastewater, and river water after an inquiry back in 2016 in Havelock North when a Campylobacter outbreak caused over 5,000 people to fall ill due to water pollution of sheep fecal matter, creating lots of toxic substances, including high levels of nitrogen. So this is an ongoing problem, and there are a lot of things that we're trying to do in order to create solutions to it, but we still haven't found an efficient one. But where is it all coming from? And why is it still a problem? Well, there are two main sources: urea, which is a synthetic fertilizer, and urine. This comes from livestock as well as our own. Now, this is a very large and complex problem to tackle all at once because of how different the sources are. But we can break it up into smaller steps and start somewhere. So we're going to focus on urine. And the people that deal with this urine is in wastewater treatment plants. Now, their job is to take the effluent and go through stages of cleaning that gets it as close to fresh water as possible before releasing it into nearby rivers. The stage that deals specifically with ammonia and nitrate removal is aeration. And we do this using what's called an oxidative lagoon. Now, these things are great. They're basically small situated ponds that are on any kind of local farm. They contain the partially treated water, which has been distilled for a while, so the sludge is sunk to the bottom, an artificial aerator that is used to oxidize the water, and something that is called as nitrifying bacteria. This nitrifying bacteria needs something like oxygen in order for the processes to occur, which I'll talk soon. And this kind of artificial aerator is a mechanical one. It basically has these fans that froth up the water and make sure that the water is oxidized. So, this nitrifying bacteria, Nitrosomus and Nitrobacter, it basically takes the ammonia and sort of eats it in a way and puts it back into another form of nitrate. And we know this process as nitrification. Now, the other nitrate form is a lot easier to be removed from waters, which is why we undergo this chemical process, and that is why it is removed at a later process. Now, this nitrifying bacteria is great because it's a biological chemical process, so it doesn't require any synthetic chemicals in order for it to go underway. However, it does require a lot of oxygen, and that's why we have those artificial aerators to try and oxidize the pond. And that is where the problem lies. Our artificial aerators are not quite up to scratch. Our artificial aerators are extremely mechanical, expensive, hard to industrialize, which means it's hard for them to be installed because of how large they are. And a lot of local New Zealand dairy farms can't actually afford to build such mechanical products. Most of the time they can't actually afford to build them. Here we have an oxidative lagoon that has been drained, and the artificial aerators are at the bottom of the pond. So what they've had to do is they've had to build this big pond, they've had to create airways, which is dug underneath the ground so that air can flow into the artificial aerators, and then a bunch of large bubbles are basically pumped up through to water. And they basically rely on the photic depth for the oxygen to try and absorb into the nitrifying bacteria before it reaches the atmosphere. And the problem with these mechanical aerators is that they often break a lot, and this requires a lot of maintenance. And when something like an artificial aerator breaks in an oxidative lagoon, someone still needs to go get it, and that's never a pleasant job. So I think it's about time that we rethink our artificial aerators. There's got to be a better way that we can create more, better, efficient, and productive aerators that maximizes oxygen and prevents jobs like that being created. And we do have something for that, and that is called the Aquarii Unit. The Aquarii Unit is a locally owned business and locally manufactured. I happen to know this because the inventor happens to be my father, and this is why I think this is a great solution. Yeah. The Aquarii Unit is a Venturi-based high-rate laminar flow aeration system. It's about as tall as me. There's no mechanical moving parts. You can put it in the back of your truck, and it uses physics and biology to maximize oxidation. And it does this by utilizing three main stages: the oxidation process, the nitrifying bacteria, and the algae that's been growing inside the oxidative pond. Now, I've been instructed not to show you the insides of the machine, but I can still show you how it works. So you have a large diffuser and a small diffuser. This diffuses oxygen. So the large diffuser diffuses these large coarse bubbles, while the fine diffuser diffuses smaller bubbles. And this is pumped through an outside air pump that goes into the machine. The large coarse bubbles are pumped up through a Venturi shaft. This creates a high-rate laminar flow, which is ejected out onto the top of the surface of the pond. Then, the fine diffuser diffuses small oxygen bubbles, which then attempts to go to the surface of the water. So, you've got this high-rate laminar flow of large oxygen bubbles going across the top of the water. The fine diffuse bubbles want to try and break that atmosphere, but because of the laminar flow, it actually stays underneath the water and travels 15 to 20 meters across the pond. And this greatly maximizes the oxygen absorption within the water. Now, the bacteria love this because they need this oxygen in order to undergo nitrification. However, they also need something to stick to. So a lot of aerators will often have large slabs of plastic or other surfaces for the bacteria to attach to. However, that's not required with an Aquarii unit. The laminar flow has been going around and it's been picking up all the sludge and the algae that's been growing on the side of the pond. So it's basically floating around now. The sludge particles actually act as the surface for the bacteria to attach to. So there's no reason to have a large piece of plastic or other substance for the bacteria to attach to because it uses the sludge particles that's already there. As well as this, the algae has been picked up and grown around, and now it's on the pond. And it actually photosynthesizes due to the direct sunlight being on the pond, which causes even more oxygen production to occur. Keep in mind, the algae is creating pure oxygen, which is 80% more pure than the air that we pump into. And all of this is used to create a state known as a supersaturated state. This is when there's as much oxygen being absorbed into the pond as possible to help maximize the nitrification process. And this is the results that has been found from it. So you can see on this graph that we have the rates of dissolved oxygen and oxygen absorption over the course of a year and a bit. Now this was done back in Canterbury and it's been tested on a nearby wastewater treatment plant. So you can notice that there's a couple dips within this. And this is due to the algae photosynthesizing. So in the day, it creates high levels of oxygen, and at night, it creates lower levels of oxygen. We know that this is because of the algae, because the Aquarii unit is running 24/7, so it has to be because of another factor. Now, when you notice, you'll start to see an accumulation of oxygen. Now, this is because so much oxygen is being produced from the algae as well as the oxidation process that the bacteria can't even use all of it. So it's currently at its full process in order to nitrify the ammonia in the water. And so an accumulation is brought up to what we call the supersaturated state. And this is where as much nitrification can occur as possible. when we're at the supersaturated state, we can turn what would be 150 milligrams per liter's worth of ammonia and nitrate into less than 3. Now this is actually funny because the measuring probes that are being used in order to measure how much ammonia and nitrate is in there can only measure 3. So as far as we know, it could actually be at 0. And this is far below the required limit before it's released into nearby waters. Now I know what you're thinking. It is a miracle machine. It's got no problems. It still does have some disadvantages. This can only be used in small systems. This is not something that you'd want to use for large cities at this point. However, with further development and research, we could get to a point in which it can be. This cannot be, it's not designed for river systems. So this means we can't take ammonia and nitrate out of the water already, but we can stop it from going in. And it still rags up. It still has problems, and it still requires maintenance, just like any other aerator. However, unlike the mechanical aerators, when this rags up, it doesn't break. So when it gets all clogged up with any other substances that go through, you can simply remove it without having to replace the whole machine. And when you compare the disadvantages with the mechanical aerators and you consider the advantages of the Aquarii unit, you can see that it outweighs most of the other ones. So, ammonia and nitrate is a rising problem. It is a current problem that's occurring within New Zealand, and there is solutions that we need to work on. Now, the sources of variation are extremely wide and variant, and we can't tackle the whole problem at once. We still have that urea, which is a synthetic fertilizer. We still have cows that are urinating directly into the river, and we still have our inefficient mechanical aerators. However, we have to start somewhere, and this is an excellent step into creating a more efficient, environmentally friendly New Zealand with fresher and cleaner waters. Thank you.
Kia ora.
Hi.
What about the production of nitrous oxide?
Nitrous oxides, that hasn't actually been explored within the Aquarii unit. The test that we've only done so far has focused on nitrate and ammonium nitrate, so we haven't actually had any tests for that yet. So we have no idea.
Do you think that might be a problem?
Well, so far, we haven't had any problem. In terms of the machine itself, it hasn't caused any damage to what the machine could do. But in terms of our tests, we haven't found any current problems that could affect it.
Just a query about your use of the Havelock North example of water pollution. Mm-hmm. It was my understanding that it was, as you mentioned, caused by E. coli.
E. coli?
Yeah.
Oh, that's interesting. Well, I have heard that there's been a couple variants of what there was, but as far as
whether it be Campylobacter, as you said, or E. coli,
mm-hmm.
what role would nitrates have in that?
Well, there's a lot of nitrate and ammonia in fecal matter and urine, so when that did pollute the waters to cause that virus to start, that caused a lot of problems. And
you think that the nitrate was responsible for the E. coli?
It was not entirely responsible for it, no, but it did have some effects.
You talk about laminar flow. Is it the laminar flow that increases the oxygenation compared with your whirling things?
No, so the laminar flow is not the sole reason as to why the oxidization works, but what it does is that you've got the large bubbles that's going across the top, right? So that's ejecting it at quite a high rate, at a high rate laminar flow. And what that's doing is it's stopping the fine diffuse bubbles to break surface tension straight away. So when you saw the mechanical aerators, that was the drain one, it basically relies on the photic depth in order for the oxygen to be absorbed before it reaches the top of the surface. But with this, it actually keeps it underneath for a longer period of time, which is why the fine diffuse bubbles can oxidize for longer.
Thank you.
Thank you.